All right, so lesson 1.2 is going to be a lot of review from last year. All of you had a pretty thorough unit on parent functions in pre-calculus, and so that's what we're reviewing very quickly today. So I just have a few examples to go over with you, but hopefully none of this is new information. Remember, there's a lot of different parent functions. The first one we're going to discuss briefly is a linear function. Just remember that functions that are linear have a constant rate of change, which means that their slope is a constant value, which means that they are straight lines. Okay, that shouldn't be new information to you. We're going to do an example just to remind you of some things you can do with linear functions. This question says, as dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T as a function of the height in kilometers, assuming that a linear model is appropriate. So we're saying, in real life, it's probably not a straight line sort of situation, but we're going to assume that it is now because it's telling us to use a linear model. So we're assuming that there is a constant rate of change. Okay, so the first thing we're going to do is we're going to recognize that they gave us 2 data points. And so those data points are when you are 0 feet off the ground or on the ground, the temperature is 20 degrees. And when you are 1 kilometer off the ground, the temperature has now lowered to 10 degrees. So that's enough information to help us with part A, with writing the equation, which requires that we first know the rate of change. And that means find the slope. So we're going to do the slope here simply by doing y minus y over x minus x. But in this case, it's t minus t over h minus h. And so we are getting 10 over negative 1, which means we have a slope of negative 10. And let's kind of identify what that means. It means that for every kilometer you rise in elevation, the temperature goes down 10 degrees Celsius. Okay? Then we could use that to help us write a linear equation to represent this situation. Remember, y equals mx plus b is the slope-intercept form of a linear equation. You know the rate of change, or the slope, is negative 10. B is the y-intercept, kind of like where you're starting if you were at ground zero, which we actually do know that value. That value is 20. So we're going to call this equation negative 10x plus 20. And actually, I'm going to stop and I'm going to rewrite it in the correct variables. The variable was the temperature with respect to height is negative 10h plus 20. Because we didn't have x's and y's, we had h and t. All right. Part B. You can look on your notes. Part B says draw the graph of the function in part A, and what does the slope represent? So we would just do something very, very basic here and say, okay, maybe we'll go, here's 10 degrees, this is the temperature, 10 degrees, 20 degrees, and then this would be the height in kilometers, temperature, degrees Celsius. And maybe we'll just go 0, 1, 2. And we're going to graph this starting with 20. And we're going down 10 over 1 as our rate of change, or our slope. So it would be something like this. That would be our graph. And it says describe the slope. We already kind of said that the slope means that the temperature decreases by 10 degrees Celsius for every 1 kilometer in elevation. It doesn't have to be exactly those words, but something along that line. right, one more part. Part C. Part C says, what is the temperature at a height of 2.5 kilometers? So all we're going to do is we're going to use the function that we wrote, and we're going to plug in 2.5, because 2.5 is the height. Feel free to use a calculator if you need one. Okay, plug in 2.5 and do the math. So we would get negative 5 degrees Celsius would be the temperature there. Okay, I'm going to do something that I don't normally do, and that is I'm going to kind of just skip through slides without writing a whole bunch of stuff down, because all of this is review from pre-calculus. If you feel like you need more review than just reading the brief descriptions, please reach out to me and I can give you some more resources. But this is basically just introducing different kinds of functions. So this is saying, hey, there's a thing called a polynomial function, which you know what polynomials are, so that shouldn't need reviewed. There are also things called quadratic functions. They are specific kinds of polynomials. These are also called parabolas. So quadratic is the name of the function, and parabola is like the U shape is called a parabola. Polynomial functions can get really fancy, crazy looking, or they can be more simplistic. A cubic function is one of those, and a cubic function is going to look kind of like an S-curve, sort of. That's a parent function we discussed last year. Here's some more of your parent functions. I think we learned the linear, the quadratic, and the cubic function, and maybe the quartic function, which is x to the fourth. But we didn't go much beyond that. You'll notice that your even functions look similar and your odd functions look similar in these power functions. Power functions means it's just a very simple equation, x being raised to some power. And so that would continue. If I had y equals x to the 999th power, it would look kind of like one of these x cubed or x to the fifth functions. Here's another comparison showing you the difference between even functions like x squared, x to the fourth, and x to the sixth. Very, very similar. And then also x to the third compared to x to the fifth, x to the seventh would look similar, and so forth. There are also things called root functions. Roots are like square roots, cube roots, fourth roots. So here's your square root function. Here's your cube root function. Those should look familiar. There are also functions called reciprocal functions. An example here is given to you, v equals c over p. This is something that we would use or see in physics or chemistry. It is a reciprocal function by nature. Here's the parent function for a reciprocal function. That should look familiar as well. Rational functions are functions that have a polynomial on top and a polynomial on bottom of like a fraction. We didn't really study these so much as parent functions because they're all over the place, but we did discuss that there are domain restrictions within things like this, meaning there are numbers that aren't able to be plugged in because it wouldn't mathematically work. For example, you can't plug in plus or minus 2 to this particular rational function, because if you did, you would get a 0 in the denominator. And mathematically, you can't divide something by 0. Trigonometry, this is where we start to kind of get to things that we did in the spring last year, so maybe not as much information retained here. But trig functions, this is going to just be a review. This is your sine function. This is your sine function. Notice your sine function does start at 0, 0 and has a max at pi by 2 and a min at 3 pi by 2. Your cosine function looks really, really similar to your sine function, except your cosine function starts at 1, has a min at pi, and a max at the origin, or not the origin, at 0. Tangent is the one that's weird, that looks nothing like the other two. Tangent looks like a bunch of those cubic functions kind of all put together. Exponential functions, you got exponential growth and exponential decay. They all kind of look the same, even if the number that's, at the base of the power changes, they still tend to look very, very similar in that shape. Logarithmic functions, same deal. The log base value may change, but the logarithmic function won't move too much in its shape. Remember, ln is also a logarithmic function. It's the same as log base e. Okay? These two are the same thing. So log base e would also be kind of in the mix there. All right, here we're getting to the point. So when we learned all this stuff last year, we did also study transformations, like moving graphs, left, right, up, down, stretch, compress, all that. We're going to do a quick review of those things in this example. So we're going to start with a parent function of square root of x. So we need to remember what that looks like. That is one that starts at the origin, has key points of 1, 1, 4, 2, and you could even go 9, 3 if you want more data points. This is your parent function, radical x. And we're just going to do some transformations and kind of move it around to get a review of how that works. So we are going to do radical x minus 2. So this first one here, radical x minus 2. That would mean shift the graph down 2 spaces. So down 2 spaces, move all these points down 2, and you have radical x minus 2. Okay, now when the minus 2 goes inside of the radical sign, that now becomes a right movement. Instead of up or down, it makes it right or left. Minus moves up or moves functions to the right 2 units. So we need to move to the right. Each of these dots to the right 2 times. That one would be off the graph. So this would be radical x minus 2 with all of it underneath the square root symbol. Okay? Negative in front of the radical is going to make that function flip. So we need to flip the function, and that's going to make it reflect over the x-axis. Okay, so that's negative radical x. And then the next one, maybe a different color here. The next one is going to make our graph stretch by a factor of 2. So that's going to mean every point on the graph is going to get taller, and it's going to be double the y value that it's currently at. So the origin will stay the same. The y value at this point is 1. Now it's going to double and be at 2. The y value at my next point is 2, so it's going to double and be at 4. And this y value is currently at 3, so it's going to double and move to 6. So everything on the graph gets taller. The last one, we have, I'm running out of colors. I just have to do yellow. That might not be very good, but we'll see. This one we have a negative on the inside. That's going to make it reflect over the y-axis. So that's going to reflect, oh wow, that's bright, over the y-axis like this. Okay. So this is just a slide to kind of review how stretch and compress works within trig functions. It's just going to make the waves taller or more narrow. Let's try transformation with our trig functions. So we are going to graph 1 minus sine x. A couple things are going to happen here. The 1, actually I'm going to rewrite this. Let's write it as negative sine x plus 1, because I think that's a little bit easier to read. This negative is going to cause my function to flip over the x-axis. This plus 1 is going to make it move up 1 unit. So let's start with our parent function of our sine wave. Sine waves start at 0, 0. At pi by 2, it goes up to 1. There's 1. Then back to 0, to negative 1, and back to 0. So this is our parent function for sine. Just regular sine. And then we need to reflect over the x-axis and shift it up 1. So I would do this 1 point at a time. Starting here, you can't reflect this origin value, but you can move it up 1. At pi by 2, I'm going to reflect it to take it to here, and then move it up 1. This pi point won't reflect, but you can move it up 1. 3 pi by 2, I'm going to reflect it to here, and then move it up 1. And then the last point can't reflect, but it can go up 1. So we've got a wave that has been transformed. So this is your 1 minus sine